Let's do a recap of what we discussed in this chapter. First of all, let me start by saying that we can classify the forces being applied on a system as internal forces and external forces. F external, we saw that leads to external work being done on the object, and internal forces were the conservative forces and the non-conservative forces. Non-conservative forces being friction, which led to change in thermal energy, and conservative forces like weight and spring force lead to a change in potential energy. So the change in kinetic energy of the system plus change in gravitational potential plus change in spring potential plus change in thermal energy must equal work done by external force um, on our system. And this change in, of course, here this whole thing is the total energy of the system. So any change in between um, kinetic and potential energies, or thermal and potential energy, or thermal and kinetic energy, is of course a transformation of energy, and any increase in the energy of the system due to work done by the external force is a transfer of energy. So external force, if the external force does positive work, then energy is transferred into the system, which means the total energy of the system goes up. And if the work done on the system is negative, that means energy is transferred out of the system, which means total energy of the system goes down. But any transformation between potential and kinetic, that happens within the system. That's a transformation of energy as opposed to a transfer of energy. So let's take a look at a few examples here. This first example is an object. We have force F acting on the object. The displacement of the object is delta S. Object has mass m, and acceleration is 0. And there is kinetic friction in the opposite direction to delta S, of course. So conservative forces don't exist because the displacement is along the horizontal. But conservative forces for the purpose of calculating the change in the energy of the system. We don't need to consider weight in this case because there is no change in the potential energy of the system. The displacement is along the horizontal. But in the true sense of the word, yes, conservative forces like weight do exist, but in this case, because displacement is along the horizontal, we don't need to consider it. Well, this change in potential energy is 0. Non-conservative forces, well, friction force is minus Fk, y minus, because this is the direction of displacement, and Fk, kinetic friction force, is in the opposite direction. So which means that the work done by it is negative, i.e. the change in thermal energy is positive. External force is plus F, which means the work done by it is positive. And the change in kinetic energy, well, since initial velocity and final velocities are equal, change in kinetic energy is 0. So now, taking a look at our mother of all equations, we have delta K plus delta U plus delta E thermal equals F external. Well, what do we have for delta K? Well, this term is 0. Delta U was 0. Delta E thermal, we said that's a positive term, and work external, that's a positive term. So what we have here is a transfer of energy into our system. Work done by external force transfers energy into our system, which exhibits itself in the form of thermal energy, okay, or a change in thermal energy. Now, let us scroll down a bit and scroll down a bit, and now let's consider the case where excuse me, we still have an object being displaced through delta S, but the object slows down from initial velocity to which it comes to a stop as a result of friction force acting on it. So once again, there is no change in gravitational potential energy of the system, and I don't see any springs anywhere, so change in potential energy is zero. Our non-conservative force is the friction force to the left, which means that the change in the thermal energy of the system is positive, since the work done by friction force is negative. Now F external, there is no F external being applied. Our object had some velocity to start with. We don't know what the cause of that velocity was, but over the interval that we are considering this situation, there is no F external being applied to the object, which means that work done by F external is zero, and the change in the kinetic energy is a negative number because change in kinetic energy is 1/2 of final velocity squared minus 1/2 of initial velocity squared. Final velocity is zero, so therefore we have a negative value for the change in the kinetic energy. Therefore, writing our equation, delta K plus delta U plus delta E thermal equals work external. We have a negative value for kinetic energy, 0 for change in potential energy, and a positive value for change in the thermal energy equaling 0. Now, so what we see here is a transformation of energy in between kinetic and E thermal. So there is no transfer of energy because there's no work done by any external force. So this is a transformation of energy, whereas up here we had transfer of energy. So when there's external work being done on the system, we talk in terms of transfer of energy to the system. Otherwise, we have a transformation of energy within the system. So now let's consider the case where we do have some change in the gravitational potential energy. What we do is, well, we pick up an object from the ground level and raise it up and place it on a shelf at a height h. So our initial position is at y equals 0, and our final position is at y equals h. Now, during this in between initial and final positions, there's a force mg on the system. That's the weight of the system due to the conservative force. Now the force is negative mg, it's in the negative y direction, which means that the change in the gravitational potential energy is positive. Well, of course, the final gravitational potential energy here is mgh, whereas here is 0. That's our UG0 level. Okay. Now non-conservative forces are 0. Let's ignore air resistance. So change in thermal energy is 0. F external. This is our F. That's the force that we apply to the object in picking it up. Well, F external is positive. Work done by F external is positive. But change in kinetic energy is 0 because the object is at rest here, and so it is up there. So the change in kinetic energy is 0. What happens in between doesn't really concern us. So we're only comparing the final state and the initial state. So change in kinetic energy is 0. A change in gravitational potential energy is a positive number. Change in thermal energy is 0. Work done by external forces is positive. Now this is another case of transfer of energy. So that the energy was transferred to the system by the work done by the external force, and it got transferred into the system in the form of gravitational potential energy. Now Excuse me. So if we now were to consider slightly uh, well, a two-phase situation where we have the object resting at y equals 0 level, so we can call this our UG 0 level, and then a force is applied to it, F, this force right there, which launches the object, and when it reaches height h1, force is no longer applied to it, yet the object has some velocity as a result of this force being applied to it, v1, and then it goes all the way up till it reaches its turning point. So v2 here is 0 at height h2, after which it turns around and falls back, of course. So let's now, first of all, let's consider this first stage. Delta k going from 0 to 1. Well, we start at the 0 velocity, and velocity becomes a positive number, v1. So our delta k going from 0 to 1 is a positive number. All right. For conservative forces is negative, which means that change in gravitational potential energy is positive, mgh1, where h1, this is our change in the height, the vertical displacement of the object, h1. Non-conservative forces, once again, are non-existent, therefore change in thermal energy is 0. And work done by external force F is positive, so we can go ahead and write delta K plus delta K, which is a positive number, delta UG is a positive number, E thermal is 0, and work external is positive. So what we have here is that the work external is now transfers energy to the system in the form of part kinetic energy and part potential energy. So this is yet again a transfer of energy into the system. So work done by the external force increased the overall energy of the system. Part of it was used up to speed the object up, kinetic energy increased, and part of it was to increase its potential energy. Now for the second part of the object, going from position 1 to position 2, this part here, the change in the kinetic energy is negative. We go from having a positive velocity to 0 velocity. So the change in kinetic energy is negative. Once again, the work done by conservative forces is negative, which means that change in the gravitational potential energy is positive. Sure enough, we go from height h1 to height h2, and h2 minus h1 is the change in this vertical displacement of the vertical position of the object over this interval. Once again, the non-conservative forces are 0, delta E thermal is 0. F external no longer exists in the second phase, so work done by external forces is 0. So writing our general equation, we have delta K plus, this is our delta U from up here, plus 0, which is our E thermal, must equal 0, which is, so this is work done by external forces, and this 0 here is the change in the thermal energy. So now you see that for the second stage of this problem, our kinetic energy got transferred into potential energy. So the kinetic energy that the object had at this level got transformed into potential energy at level 2. So this is a transformation of energy as opposed to the transfer energy that we had before. Alright, the last example I want to go through involves a spring force. So let me choose a suitable pen. What we have here is an object M resting on a horizontal surface, and the object M is pressed against the spring. So the spring, which has a spring constant K, and let's say x0 here shows the natural length of the spring. So the blue, this is the unstretched length of the spring, and which means that the compression of the spring is delta x. Okay, so our initial position, this is the initial position of the object. The object is pressed right up against the spring, and then it is of course at rest, so V0 is equal to 0. And when we let go, the spring stretches into to its natural length. That's the blue spring, the blue curly line that is on the drawing, and the object takes off with some velocity v1 along the surface. There is friction involved. This is the coefficient of friction, and if we now consider the forces acting on the object, well, of course there is weight mg, there's normal force, and there is friction force, which is in the reverse direction, and we have a spring force F spring, which is directed towards the positive x-axis. Now our general expression is given here, where we have change in kinetic energy. Our change in kinetic energy is simply 1/2 of mass times velocity 1 squared. Velocity 1 squared is the final velocity that the object has just when it leaves the spring. Velocity zero, the kinetic energy at the initial state is 0, of course. Now the change in gravitational potential energy is 0, so we don't need to consider that. Change in the spring potential energy is negative 1/2 of k delta x squared. That's because change in the kinetic energy, the spring potential energy, we go from 1/2 of k delta x squared to 0. The final US final is 0, whereas US initial is 1/2 of k delta x squared. We had these couple of lectures ago. And change in the thermal energy of the system is simply work done by friction force, and there is no external force, therefore work done by external force is 0. The only forces, the work done by normal force, of course, is 0, because it's orthogonal, or it's perpendicular to the displacement of the object. So now what I have elaborated down here is why change in delta USP is minus 1/2 of kx squared, and why the changing delta kinetic energy is minus 1/2 of m, I'm sorry, plus 1/2 of m v1 squared, and this is minus 1/2 of k delta x squared. So plugging these values in, you see that minus 1/2 of mv squared minus 1/2 of k delta x squared plus mg delta k mu k delta x must equal 0. Now this term here is the work done by friction force, or the negative of the work done by friction force. To see that, you need to note that, well, friction force is in the reverse direction to displacement. Our displacement is through delta x, that is magnitude of displacement is delta x. Now friction force, so it's a work done by friction force is equal to minus Fk times delta x, which is equal to a minus normal force times mu k delta x. This term here is simply friction force, and since we are on the horizontal surface, normal force is equal to mg mu k times delta x, which means that work done by friction force is equal to minus mg mu k delta x. But we had the negative of the work done by friction force, therefore we have to substitute in the negative of the sign here becomes a positive essentially. Okay, so now you can go ahead and solve for the velocity, because our expression has 1/2 of mass times velocity final squared. K value we know, delta x we know, mass we know, mu k is given, delta x is given, so the only unknown is the final velocity v1, which we can solve for. So it is important to pay attention to the sign of the work done by any force that you're considering. So in this case you had to be careful that friction force, the work done by friction force, was negative, and well, you should it's an intuitive answer anyhow, but please be careful in calculating work done. So friction force, once again, is given by normal force times coefficient of kinetic friction. This is work done by kinetic friction, that is kinetic friction force. So work done by kinetic friction force is simply the magnitude of friction force times the displacement and cosine of the angle between the friction force and displacement. But do remember that friction force is always in the opposite direction of displacement, which means that the angle theta is 180 degrees, and cosine of 180 degrees is equal to -1. Therefore work done by friction force is negative of the magnitude of Fk as delta x. Okay, so kinetic friction force is always opposite in direction to displacement. That's why -1, cosine of 180 is -1. To reiterate again, if you have a non-constant force, then you have to consider the area under the curve. So if you have a graph of fx versus x, that will give you work done by the force along the x direction, the displacement of the object along the x direction, so that's wx. And similarly, if there's an fy acting on the object while it's being displaced along y, then it's the area under this curve, which gives you should really be wfx and wfy. Alright, so in this case, that's change in the kinetic energy of the object along the x direction, and change in the kinetic energy of the object along the y direction. Okay, that's about it.